Welcome to the course on principles of vibration control, and we are now learning the application of the vibration control in terms of vibration absorber. So, today we will talk about the basic concept of dynamic vibration absorber, and we will try to illustrate it with the help of a model simple vibration neutralizer. You have seen a very similar thing in the beginning of the course, and you can just watch that once more, that the Stockbridge damper, which is a kind of a very simple vibration neutralizer, which is used in the power transmission. So, that kind of a systems, the model of it we will see, and we will also see some of the applications of DVA or the dynamic vibration absorber. So, let us first talk about what is the basic concept of a dynamic vibration absorber. Now, basically when we talk about a dynamic vibration absorber, this is actually system modification. This will come to that category of vibration control, and here the way we are modifying the system is by attaching a secondary mass to the primary vibrating system. What is our intention? The intention is that the secondary mass will vibrate and it will dissipate the energy, while the amplitude of vibration of the primary mass will actually come down. So, that means you have say for example, a primary mass system like this, a spring and a damper. Maybe you can also make it a Kelvin White model. So, some K, some C, very small maybe, and this is MP, and what we are doing in the dynamic vibration absorption system is that we are actually adding a secondary mass along with a spring. So, this is MS and this is a secondary spring, and there can be a secondary damper also. Depending on that, there are various classifications of such a system. So, this entire system is designed so that this system vibrates more and more and this system vibrates less and less. So, you are sacrificing the vibration of the secondary system in order to save the primary system getting a large amplitude of vibration. There are many applications of this DVA concept. For example, I told you already that vibration control of transmission cables fall into this category. Then there is this control of torsional oscillation of crankshaft in automobiles, control of rolling motion of ships, control of cutting tools, control of noise in aircraft cabin, and vibration control of handheld devices. There are many abundant applications of the dynamic vibration absorber. Now, we can classify all these applications to three basic categories. The first category is where you are adding the secondary mass to the primary with the help of only a spring element. Then it is called vibration neutralizer. So, we have once again a primary system. This is primary MP, this is K primary, and I am only adding one spring and one secondary mass. So, this is what is our neutralizer. In the second case, auxiliary mass damper, we are actually not giving this spring. So, we will delete this spring and we are going to use, instead of a spring, a damper here. So, this will then become AMD or auxiliary mass damper if I replace the spring by a damper. In the third case, we will have both spring as well as damper. So, in the third case, it is the most generalized case where you have both spring and damper, and then we are going to call it as DVA or dynamic vibration absorber. So, DVA itself has three, the first special case as vibration neutralizer, second case, vibration neutralizer by the way is also known as tuned mass damper TMD or tuned mass damper. That is also another name of the same system, and then auxiliary mass damper and then the dynamic vibration absorbers. Now, let us look into the model of a simple vibration neutralizer or tuned mass damper. A Stockbridge damper is one such example. So, here you have a primary system. So, this is the primary one, and this primary system is getting excited by a harmonic excitation, and let us say the excitation response is also harmonic x1, which is capital X1 as the amplitude times e raised to the power j omega t, and the secondary system we have added a stiffener and a spring and a and a mass, and its excitation x2 is x2 capital times e raised to the power j omega t. So, a harmonic excitation is creating harmonic response in two places, in the primary mass, this is primary, and in the secondary mass, this is secondary. Now, with this let us try to formulate the equation of motion of the system first. So, if you look at the free body diagram of the system, at each and every stage you should do that, then it will be clear to you that this is m1, that is the primary mass, it is subjected to a dynamic excitation, let us put that force f e raised to the power j omega t, and its excitation is in this direction. So, this is your excitation x1 equals to x1 e raised to the power j omega t. What it means is that there will be an inertia force which will be in the opposite direction, and it will be m x1 double dot m1 in this case, and also it is going to have a spring resistance. So, let us draw the other resistive force here, that is k1 x1. So, these are the total the forces working in the system, and of course, there is another force that will be coming from this k2, we cannot neglect that. So, let us put that as k2 x1 minus x2, that is the relative displacement between the two. So, now our things are complete, this is the total system. So, that means if I look at the equation of motion, summing up all the forces m1 x1 double dot, that is this force, then k1 x1, that is this force, plus k2 x1 minus x2, that is this force, all these three should be equal to the force in the right hand side, which is external force f e raised to the power j omega t. What is happening for m2? Well, m2 does not have any external force, m2 only has the inertia force, which we will put as a dotted line m2 x2 double dot, and also the resistive force from the spring, which is just equal and opposite. So, it is k2 x2 minus x1. So, that is how this expression is coming up. So, this is the governing equation of motion of a simple vibration neutralizer. Now, in the steady state, let us apply x1 as x1 e raised to the power j omega t and x2 as capital X2 e raised to the power j omega t, because we are only looking for the steady state solution. If you do so, then e raised to the power j omega t will get cancelled from both the sides, and you will get these two algebraic expressions in which you will have x1, x2 and f. So, x1, x2 will be the two unknowns, and there are two equations, we should be able to find them out. So, if I solve it, you will get x1 as f times k2 minus m2 omega square, and the denominator is k1 plus k2 minus m1 omega square times k2 minus m2 omega square minus k2 square. And in the second case, for the secondary mass, the denominator remains the same. So, it is the same denominator, the numerator becomes f times k2. So, what happens when, for example, your k2 will become equal to m2 omega square. Okay. That means, omega square will become k2 over m2. that means omega will be square root of k2 over m2. That is the natural frequency of the secondary system. So, if I use this condition k2 equals to m2 omega square, then what we will see is that in this particular case corresponding to this condition x2 would become minus f over k2. So, that means there is a displacement in the secondary mass x2, but what is going to happen to the primary mass? If I apply k2 minus m2 omega square 0, this will be 0, this will also be 0. So, that means it will become 0 minus 0 over k2 square. What it means that it will be 0. So, that means if I can match the omega is nothing but the excitation frequency, so if I can match k2 and m2 with the excitation frequency, then we will have a case where we will have actually response of the secondary mass, but no response at the primary system. That is the objective of such tuned mass damper. So, that is what we are also telling in the same case. So, the primary system comes to rest. So, that is the major conclusion, that the primary system comes to rest after the tuning of the system, provided you know what is the exact excitation frequency of the system. You need to have a sensing for that, or somehow you need to estimate it properly. Now, what are the design considerations for it? It should be noted that a tuned neutralizer makes the response of the primary system 0 only at one frequency, that is at omega 2. So, the application of such a neutralizer is very much limited. There are some cases which we will see where we can change this, but in this case definitely it is very much limited. And even though the tuned mass damping could successfully neutralize the vibration response of the primary system when the excitation frequency is omega 2, it also introduces two new resonating frequencies to the original system. So, there should be care that these two new frequencies are actually sufficiently away from expected excitation frequency. Otherwise, there will be a high resonance in the system. And finally, one may note that even though x1 is 0, displacement of the primary system, displacement of the secondary mass is not equal to 0. So, there is a kind of a you need to give the space for this displacement, and that space is also known as the rattle space for the system. So, these three conditions are to be kept in mind. That means, if I look at this system, so omega versus the transfer function, then our initial system was something like this, and once we have applied these kind of a tuned mass damper system, then our system's frequency response will have actually two peaks. And if we are successful, somewhere in between we will be able to neutralize or damp down the vibration. But these two frequency existence should be thought of, so that this distance must be kept as far away as possible, so that your excitation frequency should come somewhere in between. These are the tricks that we have to think in terms of the design considerations. Now, let us look at the application of these dynamic vibration absorbers. Well, the first one is because it has the frequency limitation we have seen. Now, the self-tuned type of pendulum neutralizer can actually take care of it. So, it can deal with where there is a possibility of change of excitation frequency. The example is that there is a you consider a case of a multi-cylinder engine, then the time period of the variation of this the turning moment depends on these three parameters: the rotational speed of the engine, and the number of cylinders, and the nature of the operating cycle, whether it is 2-stroke or 4-stroke. So, this dynamic turning moment that will come out will give to the torsional oscillations of the crankshaft, and let us see how we can control it. Now, we will discuss the case of self tuning. In this case, so the excitation frequency, depending on whether it is a 2-stroke cycle or a 4-stroke cycle, it will have an alpha, that alpha equals to 1 or half, and then you have n, which is the number of cylinders, and then you have n 0, which is the rotational speed of the engine. If you neglect all the higher harmonics, that is a very simplified version of the primary excitation frequency that can come to a multi-cylinder engine. Now, you know that for a gravity pendulum, so suppose you have a gravity pendulum like this and it has a length L, then its natural frequency is square root of g by L, which it actually signifies is that the numerator is nothing but the acceleration. So, you compare that with this particular case where there is a kind of a rotational thing happening in the system with a rotational speed of n 0 as we have shown here. So, then this acceleration g will be replaced by n 0 square r, and the natural frequency of this centrifugal pendulum would then become n 0. If I just apply this n 0 square r here, then it would become n 0 square root of r by L, and then comparing this equation with our equation 1, because this is what is the natural frequency of one such system. If I add it here, it is a pendulum, except that the gravitational acceleration I am replacing it by this n 0 square r, and then the natural frequency of this system is coming out as n 0 square root r by L, and if I equate 1 and 2, then I am going to get a condition for which you can see that the condition for which this will happen is when r by L will be alpha n square. So, that means alpha, for example, for 2-stroke cycle alpha is 1 known to you, number of cylinder is also known to you. So, that means r by L is actually known to you, and if you choose also you see r is known to you of where this thing is happening, this radius of this cylinder is known to you. So, it is only choice of the length, and you can choose, you can find out the length from this equation, and then irrespective of whatever is the frequency of excitation, this system will always remain tuned. That is the beauty of the self tuning system. This is a Hudale damper, and in this of course, there is a damping constant that is involved in it, because this part in a Hudale damper is actually filled up by viscoelastic fluids. So, if mu is the viscosity of the fluid, then we get this type of a damping constant for the system. Of course, strictly speaking, this is a case of what you can say it is a case of auxiliary damper, because it is the damping that is coming into the picture. In yet another case, we have the damping of handheld devices like say for example, electric hair clipper. In this case, the excitation is coming mainly because of the power supply, which is about 60 hertz. So, as this excitation is happening, you can add a tune mass damper. You can actually see that almost all such hair clippers will be coming up with some or other form of this tune mass damper, which can actually take care of this particular excitation frequency. The driving frequency here is fixed. So, design of a tune mass damper or a vibration neutralizer is very much possible in this type of a case. What we are going to show now is that once you have a beam and it is mostly an undamped beam, we are going to show that how it can get affected by harmonic excitation. Particularly what we will see is that once that harmonic excitation reaches close to the natural frequency of this particular beam, we will see that the resonance is going to occur in the system. Very much similar, what we will also see that happens in practice in very much in various types of other structures like power transmission cables or like machines, etc. Now, we will first show that how this excitation is affecting the performance of the beam, how the resonance is happening, and then we will show that once we attach this special system to it, which is called a tuned mass damper, we can control this excitation, we can control the response of this system and bring it down. So to begin with, what I request Mr. R.K. Singh is to remove this additional mass now from the system. Please remove it, and we will see that what is the natural excitation of this beam without any additional mass, which we call tuned mass damper, without the addition of that. We are going to see this system.
No, we have removed these masses.
Now
we will start the system and you can see what is happening.
As we can see here, that this motor is actually giving an eccentric harmonic excitation to the system, and during that load we can see that the beam is getting gradually excited, and the frequency we are controlling from here, and we will be gradually reaching a frequency which is close to 7 Hz. 7 Hz is the fast natural frequency or fundamental frequency of this system, where we will see that the resonance will happen.
Yeah, now you can see it is achieving that natural frequency.
What is the frequency right now?
6.98.
So we are right now 6.98, we are approaching 7 Hz, and as you can see that the fast mode of the beam vibration is becoming very much apparent, and you can easily imagine that if this kind of an excitation happens to any structure, any bridge, any machine, then naturally the machine would not be able to resist this vibration. So our motto will be how to resist this vibration amplitude. So now what we are going to do, we are going to excite the same system but with the help of these additional masses, and we will show that how it can control the vibration. We have attached these two additional masses and we are going to excite the system. As we can see, initially both the system is vibrating, because this type of an arrangement is only effective very close to the fundamental frequency.
Yeah, we are having 6.98.
So we are at 6.98 Hz, and as you can see that there is no vibration apparent in this beam. Why? Because the entire energy from the primary beam has been transferred to the secondary, and the secondary beam with these masses, that is vibrating while the primary one is set. This is one strategy of vibration control which we will teach in much more details in this course, and it is known as a tuned mass damper based vibration control. What I am going to show you today is a fantastic application of vibration control which has been originally designed in 1920 by Stockbridge, and it is named after him as the Stockbridge damper. Now this fantastic damper, if you can see that this is a busy highway and there is a high voltage power line which has just crossed it, and on this high voltage power line you can see that with each of these high voltage line there are a pair of this Stockbridge damper which is attached to it. The way this Stockbridge damper helps to control the vibration is whenever there is a vortex induced vibration that comes into these wires, which happens in a pretty big frequency range from about 5 Hz to 150 Hz, then this vortex induced vibration creates a huge change of amplitude in the wires, and it can actually destroy the wire, it can create a huge power problem. Now this Stockbridge damper, which essentially has two additional masses hanging with the power line with the help of a messenger cable, this works exactly like a tuned mass damper that I have shown you in the laboratory, and this tuned mass damper system absorbs this Aeolian vibration, the vortex induced vibration of these wires, and keep these wires very steady so that they do not give up, and as a result a continuous power supply is possible in the system. So this is a fantastic application of the vibration control with the help of tuned mass damper system. So this is where we will come put an end in today's lecture. In the next lecture, we will talk about modeling of a system with DVA, and we will also talk about transmissibility and relative transmissibility of a system with DVA. Thank you.